Okay. Then I think I'm gonna hit my button, and then we're gonna get started. Hello, everyone, and welcome back from lunch. I trust that the lunch was amazing because it usually is at Rebel. So enjoy it while you can. And yeah, I think the more and more sessions that I see during this conference, I feel like this conference is like the perfect conference for me. There's been a talk about point and click games. There's been a talk about retro computing, and there's even been a talk about Git, and then just things that I just love hearing about. So if there's a talk about retro gaming later, then I'm like, oof, that's too much for me. But I'm gonna talk about video. And the thing that I've come to realize is that more and more things around us are video in some form or another. Instead of reading tutorials when we want to learn stuff, we typically watch YouTube tutorials. When we communicate, we use FaceTime and video instead of the normal just calling. And and even the news will autoplay videos when we browse online. And at work, you might, instead of taking only screenshots or describing to colleagues with text, you might take some sort of screenshots screen recordings. And most of us are probably more than super used to video conferencing and like hanging out online. And in my experience, people normally think of video as this black box. There are some vague ideas about formats and compressions, and that in order to edit video, you need to use a professional editing software. And there are definitely reasons to do that, but what I want to show you now is that video might not be as magic as you might think. And the goal here is to remove some of this mysticism and talk a bit about how digital video actually works from the ground up, and introduce you to some tools that you can use in your day-to-day as developers to actually hack on video, which is pretty cool. This talk is actually a compressed version of something that I did on JavaZone, so I've tried to kind of pick out what was most fun. So we'll see how that goes. Anyways, just a short some stuff about me. My name is Benedicte. I have been a developer for 10 years. I sing in a choir. I have 2 big dogs at the farm at home. I play a lot of video games. This is a screenshot from Flåklypa, I think, the game when it came out. And also retro games, which is, why retro games? But the question is, why am I talking about video? I've never worked with professional video like as in cinema or production or anything. But this story started back during Corona. With that I wanted to improve my VC or video conferencing setup. So I spent all my paycheck on fancy like audio equipment and hacking on stuff. I ended up on Twitch for a moment, played some games there, and it was a great time, the Corona part aside. So that's why I'm here today. So let's start with some theory first, and let's start with the basics. So this is an image that I've generated with AI, and we all know kind of that images are basically a table with pixels. So if we zoom in on this image, we zoom in on the image, we see that we get these squares. And this is kind of like the essence of how an image is represented. We have these squares called pixels, and every pixel is represented by a number telling us which color this individual block of the image is. So in essence, all images are pixel art. And you can refer to each pixel as a function of the amount of red, the amount of green, and the amount of blue in the square. And you can represent those colors with like more and more accuracy, making it into bigger numbers, meaning it will take up more space when you store it on the computer. And if you divide it up into the individual coordinates, this is kind of what it will look like. This is the same screenshot from the previous slide. But did you all know that there are other ways to represent this? you don't have to make it a function of red, green, and blue. You can make it a function of something called luma, blue projection, and red projection. And that the only thing that's actually different is how you put the numbers together in order to end up with the resulting color. The con that you get with this is that you need another step at the end to actually display the image on your screen, because how screens work in like the physical space is that they have a physical red, green, and blue component, a bit dependent on what kind of screen you have and so forth. But storing the image in this coordinates, or kind of this color space, means that we can take a lot of shortcuts in the digital space, meaning it's easier to compress it and kind of save data. For example, you see that there is a lot more movement or a lot of more detail in the luma part of the image. And that means that, and this normally happens with most images, and it's something about how our eyes work. So, and that's why it's so smart. You can store or you can save data by removing pixels from the blue projection and the red projection, kind of merge 4 and 4 together. And to your eyes, the image will look kind of the same, but you will have saved a lot of data. So this is the basis for a lot of image compression, and as we will see later, a lot of video projection or video compression as well. And if we move on from images to storing actual video, video is just moving images. We use a hack in the humans called beta movement, where if you see a lot of pictures after each other, then they kind of get fluffed together and you get this movement, this illusion of something actually happening in front of you. And for a typical cinema movie, you have 24 images per second, or you have 24 frames per second, which is what we call it in video. And that's a lot of data, so that's why we need these shortcuts to kind of not have to store everything. So if you take an example of a video file, it might look something like this. You call it myvideo.mp4. And most people kind of only think of it as this, that MP4 is telling us what kind of file this is. But what's interesting with video is that this doesn't necessarily tell us anything about what is in the video file. We have, imagine that you have an old roll of film, like on the old cameras. In order to take an image, you let light onto that film and you stored it. But you could use a whole lot of different types of film, a lot of different types of material. Video cameras could, for example, choose to record images in a vertical way or in a horizontal way. But still, you put image on film. And there are a lot of parallels with this in how we represent video as well. Because that same file that we looked at earlier, it could have a video track, which is stored in one format called H.264, but the container that it's put in with the .mp4 is what kind of envelops it and stores it. So if we go back to the analogy with film and image, the H.264 part is how we would store the image that was put on film, the actual data, the pixels, but the container is what kind of film we put it on, which is very interesting. And in video as well, we normally have audio because telling us what happens, and that kind of comes in addition. So the container would have to support that as well, making sure the computer plays the video and the audio together in a synchronized way. And in order to kind of translate from and to these video formats and these container formats, we use something called a codec. And codec stands for encode and decode. And a codec is basically a program with two functions, one that takes raw image data in and returns data on the format kind of way. Say if you have H.264 and you encode it, you take raw video data in, and you put H.264 data out. And then, on the other hand, you have the decode function, where you can do exactly the opposite. So if you have a file with H.264 video and you want to play that, your computer has to look up the program or the codec for decoding that H.264 data and display it on your screen. So whenever we talk about digital video, a lot of people talk about codecs very soon. And some examples of codecs are AVC and ProRes and AV1, and they have a lot of different qualities to them. You've probably heard about ProRes if you watch the iPhone announcements, for example. Apple are very into that. And ProRes is an example of a codec that doesn't necessarily spend that much effort in minimizing how big a video file is, but it will instead make the file bigger and make it easier for you to edit it. So if you put it into something called DaVinci Resolve or any kind of editing software, you'd see that scrubbing back and forth and stuff will work more efficiently because the format itself will help you along and have all the data you need ready for you, make it all fancier. And if we look at container formats, they typically look something like this: MKV, MP4, AVI, and MOV. And the pros and cons of those are basically just what you can put in it and what kind of devices it will run on. And another interesting thing is that, and this was in relation to the, I think I have to go back to the container stuff. And yeah, you know what? I forgot that whole line of thought right now. But anyway, if you wanted to know how you would program menus on Blu-rays, this is how you do it. And I mean, the last time I held this was at Java, and the way you program it is with Java, so I felt I had to mention it. But anyway, that's it. So let's continue on here. I want to show you a bit about how you can take a video file that you have and actually see what's inside it. And to do that, you can use a command called ffprobe. This comes from a project called ffmpeg, which we're going to talk about later. So you call ffprobe and you put a video in. And this is a video that I recorded with my iPhone. And you can see there's a lot of information here, and it's very overwhelming unless you know what you're looking for. But the interesting part here is from stream 00, which is our video stream. We talked about containers, and the different tracks in a container are also known as streams. And we can see that it's video here. It's encoded in the H.264 codec. High is the profile. It has profiles for main and high, and those are basically just different versions of H.264. I think I forgot to mention that even though I've spent a lot of time looking into how video works and kind of scripting it with FFmpeg like this, I still feel like every time I try to study some of it, I feel so stupid because there's always something else that I don't understand, like on a deeper down level. It's the true definition of an iceberg. But yes, H.264, and you also see there mentions of the YUV420p on line 11 there. And we talked about the color spacing. And imagine that you have 4 pixels in the luma space, like the one that was leftmost, where we are most sensitive, our eyes are most sensitive. But those same pixels, you only use 2 pixels in the red projection space. Because you merge all of them together, so you kind of just use the same number. And in 0 means that for the last one, I think it was the red projection, you don't use any at all. You just have the same value. This is something called chroma subsampling, and I'm sure you've heard about it if you've seen any videos about how video works in general. A lot of systems will talk about chroma subsampling and all, but what it basically tells us is a built-in way of compressing video, which is interesting. If we instead go to a file called, or a file that I also recorded with my iPhone, but this time I pushed the button for ProRes, which is Apple's fancy codec, and we can see that ProRes is indeed the format that this video is stored in, and there's a variation of ProRes called HQ, which is like high-quality ProRes. And we also see that it says YUV422p, and just ignore the numbers after that. It just means how many or how much precision you use to store the numbers. But 422 then means that for every 4 luma pixels, you have 2 of the blue projection and 2 of the red projection. Yes, so I added this slide because because heavy subject, and because the last time I held it at the AdaCon, it was the end of the day. It was the last session, and still there was a hardcore gang that showed up. That was very fun. But yes, I thought we would just stop with the theory there and just talk about some funny things. A Have you ever seen this happen? It's probably a bit difficult to see. But at some point, this video will suddenly become clearer. And I'm not sure if you're able to see it, but trust me, it happens. Or maybe I turned off the throttling there. Are you able to see it? No, okay. But you've been watching YouTube, you see it, it goes from blurry, it maybe stops being blurry, or it goes back into blurry. And this is something called dynamic adaptive streaming over HTTP. And what's so interesting about it is that the change in quality will happen kind of by itself. It's not a part of the JavaScript framework or how the DOM works or anything. It's actually part of the video. The video that you're watching is being changed right in front of your eyes. It's kind of like that GIF from Wallace and Gromit, where they're kind of laying tracks as the train goes. And this protocol that they call Dash is the basis for how most streaming applications work, Netflix and YouTube and Vimeo and all of those. And the cool thing about it is that in previous times, we used to have these proprietary formats and connections that was sold by video companies, and they wanted to have this proprietary. But Dash is a different way of doing this over just normal HTTP. And what's cool about that is that you can basically put your file on a file storage or an Nginx server somewhere, and you can point a browser to it, and it will kind of just work by itself. You don't need additional software for states. You can just host it. You can use CDNs like Cloudflare to host video, which makes you can take a lot of shortcuts. And what it basically does is that you have the source video like this, and you have encoded it into different qualities. And then you split it into chunks like this, and the normal built-in commands that you can use for this. And you then provide some sort of HTTP API where the client, the browser, and the browser is in full control over which quality it wants to show. And you give it a manifest where the qualities are, and it will kind of just choose its own path depending on where you are, how good your internet is, and bump you up and down. And you can see this in the Chrome DevTools, just on the amount of network transferred. So there it goes. That's how you see it. So that's pretty cool. And all of this is done by a cool project called FFmpeg. FFmpeg is a collection of those codecs that we talked about, and it has a lot of history. I'm not going to talk so much about it, but everybody loves FFmpeg, and it's kind of powering most of all video things. It will run in VLC if you use that. It will run in NRK. I'm sure uses that at some or parts of its chain. A lot of projects use it. I think even Teams has FFmpeg somewhere down. It's an old open source project that is used by so much. And how you use FFmpeg is very interesting. It's even pretty aware that it's not easy to use. You see that filter complex. It's not even trying to lie to us. It knows that it's pretty complicated. But what's interesting about this is that you can use these commands and these parameters to do very advanced stuff with video. One of these commands, for example, will take one video and put it, scale it down a bit, put it in the corner of another video, and then put a cover image at the start, so for 3 seconds, and then produce the output to a third video file. And there's basically no limit to what you can do with this. And just some tidbits while we still have time. Video for video games. I need to talk about video games now that I'm actually on stage. If you start FFmpeg and you list what kind of formats it has available, you'll find a strange amount of video game studios from like the 90s and early 2000s. Konami was there, Bethesda is there, Westwood is there. And what's interesting about that is that we talked about how codecs could be used for different use cases. And imagine you're developing a game. A game needs to be very efficient in the system resources that it uses. So you don't want it to spend time when it's going to play a video in there. So then you could adjust or design your own codec to be that kind of efficient. And that's what they did, I guess. I'm struggling with finding more information about this, but it's so interesting. So if anyone knows anything about that, please come over to me. And I'm pretty sure that this is how Westwood made this video. So yes, and there are a lot of other cool tools that are built on FFmpeg. You have a library for JavaScript where you can like declaratively make video. You have a project that's written in WebAssembly, so you can basically transcode and convert video directly in the browser or force your visitor to do it, depending on what you want to do. And you also have this cool editing thing that's made by a Norwegian, actually, so go look it up. And what was this? Yes, if you want to make your own video player with C, there's a tutorial where I think he promises you can do it in like 10 minutes, but depends on how much C you've written, I guess. And then I just want to leave you all with this.
Read codec? The taste of a codec? Most people go into, I don't know, iMovie to do a quick edit and then export for 20 minutes. They haven't heard of FFmpeg. In FFmpeg, 2 minutes. Proprietary codec. The codec can just code it in FFmpeg. Does it really exist? FFmpeg uses multi-threading by default. So efficient. Power of open source.
So at this point, FFmpeg is kind of like a cult. They say that if you can't encode it with FFmpeg, does it really exist? I want to thank you all for listening to me ranting about this weird topic. I want to thank all the organizers for putting this great conference on. And if you want to talk about video, find me after, because I will be at Skråplanet. Thank you.